So the next container that we will be learning is list. Now list is exactly similar to vector, but the only stuff in list is it gives you front operations as well. Now list is a container, again dynamic in nature, same way of declaration. You can push back 2, you can emplace back 4. So this is the list that will happen if you push back 2 and 4. And after that, if you say push front, this front goes over here 5, like it directly pushes it into the front. In vector, you had to use the insert operation, and if you're inserting somewhere, that does take a lot of time. Like insert function in a vector is very costly. Like we will read about time complexities in further data structure algorithmic lectures, but as of now, just remember an insert in a vector is costlier. And in list, since the internal operation is a doubly linked list, like a doubly linked list is maintained for a list, and for a vector a singly linked list is maintained. So thereby something like push front is very, very cheap in terms of complexity, time complexity wise, when you compare it to a vector. Okay, and there is emplace front as well. All of the functions, begin, rend, reverse end, size, clear, empty, all of the functions are similar to vector, so I'll not be explaining that. Okay, so that is about list. Now the next container that we will be talking about is dequeue. Again, similar to list and vector, you just declare it, push back, push front, pop back, pop front, back, front, and all of the functions are similar. I'm not going to explain this as well. It is exactly similar to list and vector. So the next container that we will be learning is stack. Now stack is something as LeetCode. LeetCode means last in, remember this, last in, first out. The guy who went in last is the guy who will come out at first. So generically you can just imagine a stack to be a data structure like this, and this is how you declare a stack. Stack, the data type and the variable name. Okay, so I've declared the variable name like this. I'm saying push 1, so I push 1. I'm saying push 2, I push 2. I say push 3, I push 3. I'm again saying push 3, I push 3. I say emplace is similar to push, so I say push 5. Now these are the push operations. Right after that, if someone says stack.top, so as I said, who's the last guy who went in? The last guy that went in, is nothing but 5. So this will print 5. Yes, this will print 5. Now realize this over here, indexing access is not allowed. You cannot say this is index 0, this is index 1. Something like this you cannot say. In stack, there are only 3 functions. One is push, one is pop, the other one is stop. All other there like size, clear are there, but these are the generic 3 functions that you have to deal with. So if I'm saying top, it gives you 5, but the 5 is still in the stack. The 5 is still in the stack. Now the moment I say pop, it deletes this from the stack. Now 5 is not in the stack. Now if I'm saying top, right before 5 was there 3, so it prints 3. Now if I'm at this moment saying stack.size, there are 4 elements, so I print 4. If I'm saying stack, is the stack empty? The answer is false. It has 4 elements. Now if I'm saying swap it to some other stack, I declare another stack 1 and I say, can you please swap it? So swap is very understandable. Both the guys will swap. So I hope push is clear, pop is clear. Pop means delete. Top means just tell me what is at top. You don't need to delete. Just tell me what is at the top. So that is how the stack STL works like. Now talking about complexity wise in stack, all the operations are big O of 1 operations. Everything happens in constant time. So let's learn about the next container now. Now the next container that we will be learning is a queue data structure. Now a queue data structure is similar to stack, but over here it is FIFO. Okay, FIFO means first in, the guy who gets in first comes out first. Stack was last in. Okay, now you can just think it in this way. Like if you're forgetting names, you can say like you go into a platform and if you're buying a ticket, what do you generally do? The person comes in, the first person who comes in stands, and the next person who comes in and stands. So it's the first guy who gets the ticket, this guy, then this guy gets the ticket, and if someone is coming, it's a queue that happens. So that is where the concept comes in, first out. So if I'm saying push 1, I push 1, push 2, I push 2, push 4. So I pushed 1, 2, and 4. And the next line I'm saying q dot back plus equal to, but back will mean 4. It does not mean this guy. Back will mean 4 only. So over here I'm saying add plus 5. This makes it 9. I'm now saying q dot back. So if I'm saying q dot back, it prints the last guy 9. Okay. If I'm saying q dot front, prints 1. Just prints, does not deletes. If I'm saying q dot pop, deletes the front guy, first 10 guy. Q dot front is now 2. So it prints 2. It is similar. And now all the operations are much more similar to stack size and all these things. That's how Q works. Again, all the operations are happening in constant time. Now, the next thing that we will learn is priority queue. Now, as the name recommends, priority, the guy who has the largest value stays at the top. It's similar to queue, but there is something that happens inside which you learn probably after a couple of years when you are appearing for interviews. But as of now, just understand the logic. Okay. So remember, if you're declaring priority queue like this, the maximum element stays at the top, or the largest element. If you're using character, the largest character. If you're using integer, the largest integer. If you're using the string, the lexicographically largest string will stay at the top. Okay, so I'm saying q dot push 5. So you push in 5. I say q dot push 2. So you push in 2. I say q dot push 8. So you push in 8. Now I say q dot push 10. So you push in 10. Okay. Now the moment I say pq dot top, out of all these elements, which one is the largest? 10. So it prints 10. And that is the guy who will be at the top. Now if you are trying to insert something like 3, the 3 will go right here. The 3 will go right here. And this is not a linear data structure. Inside of it, a tree data structure is maintained, which you'll learn in the later half. Now, understand one thing, the data is not stored in a linear fashion inside. Inside a tree is maintained, okay, which probably you'll learn someday. Okay. So as of now, if I say pq.pop, the topmost element is popped, 10 is popped. If I say again now pq.top, who's the topmost? 8, yes. So this is how the priority queue works. Again, push, top, and pop. Main functions, the other ones are size and empty. Size and empty is very simple, and swap is also very simple. So these are the functions. What if I want a priority queue which stores the minimum element at the top? Then this is how the syntax is. Priority queue, data type, vector, and this greater int you have to write. And if you give this data type, and now if you push 5, 5 is there. If you push 2, 2 is there. And if you push 8, 8 is there. If you push 10, 10 is there. But this time if you try to access pq.top, 2 will come out. So that's how you maintain a very simple minimum priority queue. And generically it's known as mean heap. And this is known as max heap. Remember this, the terms that you learn in DS algo as you move forward. What is the time complexity of push? Push happens in logarithmic of n. Top happens in big O of 1. And the pop, which is the deletion, again happens in logarithmic of n. So this is how it happens. If you don't know what is logarithmic of n, no issues. Just keep this in your mind as you move forward. You will understand in DS algo. Now the next container is very, very interesting, and that is nothing but the set container. Now what is set? Just remember one thing. It stores everything in the sorted order and stores unique. Just remember these couple of points and you know what is a set. Everything in the sorted and just unique. Just 2 points and you're done. Let's understand. So imagine this is the container, okay? And I say insert 1. So you insert 1. Imagine you say emplace 2. So you insert 2. Imagine you say insert 2. Unique. So will it store 2 again? No, it does not. No, it does not. It does not store 2. If I say insert 4, will it? Yes. If I say insert 3, it will. But it will insert it here. Again, a very important thing. Sorted. Stores in a sorted order. At first, it will have 1. Then it will have 2. Then it will have 3. Then it will have 4. Everything in the sorted fashion. So it stores everything in the sorted fashion. So this is how the set will be storing. Again, a container. Is it a linear container? No, a tree is maintained. So I'm just explaining you this via this bucket. But inside of this, there is an entire tree which is maintained. Again, which you'll learn as you move forward. So insert emplace works in a similar fashion. Sorted and unique. Okay. Now there are functions. If I say set.find 3 and this is the set. So it will return an iterator. Remember this. Returns an iterator which points to this tree, which points to this tree. It returns an iterator which points to this tree. Okay. So basically this is an iterator. Remember iterator points to the address. Perfect. Now if I say set.find 6, is 6 here? No. If an element is not in the set, please hear me out properly. If an element is not here in the set, it will always return set.end. That means an iterator which points to right after the end. Imagine the set is having 1, 2, 4, 5, and you did set.find 3. Okay, and you don't have a 3. So you will have an iterator end. This is the iterator which points after 5. After 5. That's where dot find will return the iterator to be. It points afterwards. Okay. And after this, there is set dot erase. Very simple. Erases this guy 5. Erases this guy 5 out of it. Like if this is the set,